Assalamu alaikum dear students and welcome back. Today we are going to explore another essential technique in linear programming which is called two-phase method. So we have already learned Simplex method, which is widely known for solving optimization problems, but it can sometimes struggle when we do not have an obvious feasible starting solution. That is, when we have a model containing constraints which are equations or of the type greater equal inequalities. So this is where the two-phase method steps in to save the day. The two-phase method is structured approach designed to handle cases where the problem has no readily available basic feasible solution, as we have discussed earlier. It essentially breaks down the process into two phases to first find a feasible solution and then proceed to optimality. So in phase one, the goal is to identify a feasible starting solution by introducing artificial variables. So in this phase, we minimize the sum of artificial variables to achieve initial basic feasible solution for the original problem. So if we can eliminate the artificial variables by the end of phase one, then we move on to phase two. And this phase is invoked to solve original problem, where we apply the regular simplex method to find the optimal solution. So in phase one, we start with the problem by putting it in equation form and add the necessary artificial variables to the constraint, as we did in M method, to secure a starting basic solution. And from a new objective function that minimizes the sum of all artificial variables, regardless whether LP is maximization or minimization. So in both the cases, we have to minimize, initially in phase one, we have to minimize sum of all the artificial variables under given constraints. So if the minimum value of the sum by the end of phase one is positive, then the LP has no feasible solution and we will stop here. Otherwise, we have to proceed with phase two. And in phase two, we use the feasible solution from phase one as starting basic feasible solution for the original problem. So let's learn the process step by step with the help of an example. So this is an example where we have to minimize this objective function z is equal to 4x1 plus x2 subject to these constraints. One of the constraints is equation, second constraint is greater equal inequality, and the third constraint is less equal type of inequality. So first of all, we have to transform this into equation form. So this is the equation form of the system. And in this case, you can see that this is equation, so it remains as it is. Second is the inequality of this greater equal type. So we have to subtract a surplus variable, and which is x3 in this case. And in third, we have to add a slack variable to obtain an equation, and that slack variables is x4, and all the variables are non-negative. So this is non-negativity condition. Now by adding artificial variables, we have these equations. So we have to add an artificial variable in first equation and in second equation, so that we can have initial basic feasible solution to start with phase one. So this is the phase one. We have to minimize sum of artificial variables under these constraints using a simplex method. So let's construct initial tableau of the simplex method. So this is initial tableau of the simplex method because we have this equation r minus r1 minus r2 is equal to 0, and we have all these constraints. So this is the tableau, but again we can see that r is equal to r1 plus r2, R1 here is 3 initially and R2 is 6, and this makes R is equal to 3 plus 6, which is equal to 9. But in this case we have zero solution. It means this objective function rho is not consistent with these initial basic variables, so we have to make the system consistent, and for this we have to substitute R1 and R2 out of this objective function. And again we are going to same process we learned in M method. Here R1 is equal to, from this we can see R1 is equal to 3 minus 3x1 minus x2. R2 is equal to 6 minus 4x1 minus 3x2 plus x3. Plug in these values into this objective function. So we have R is equal to, add both of them, we have 9. We have minus 7x1 minus 4x2 plus x3. So objective function equation becomes R plus 7x1 plus 4x2 minus x3 is equal to 9. So now this is our new R row. So here must be 7, 4, negative 1 and 9. So let's see. This is the new row. So 7, 4, negative 1, and rest of the variables have 0 coefficient, and we have 9 as solution. So now this is consistent with these initial basic variables. And next we have to find optimal solution, and we'll use simplex methods iterative process. And for this, first of all, since this is minimization problem, we have to minimize R. We need to find a coefficient which is most positive so that we can determine entering variable. And in this case, we have this 7, which is most positive in this row, which is the objective function row. This indicates that x1 would be entering variable. Now, in order to decide leaving variable, we have to find ratios. So 3 ratio here is 1, and similarly 6 over 4, which is equal to 3 by 2, 1.5 you can write, and here we have 4. So least one is this. It means leaving variable is R1. Now, again, we have to do the same Gauss-Jordan row operations in order to get this new solution. So R1 is replaced by x1 because x1 entered basic variables. So new pivot row is this. We just divided this row by 3 in order to make this element 1, pivot element 1, and we have this row. And in order to fix this column, we have to do the row operations as we learned in simplex method. So let me show you the resulting R row. So this is the R row, and this is obtained by using row R minus 7 times this row, this pivot row, new pivot row, which is row x1. Similarly, we can perform the row operations. We have to fix this row. So row R2 minus, we have 4 here, 4 row x1, that is the pivot row. Similarly, for third equation, we have to perform what? We have to do row x4 minus, we have 1 here, so minus row x1 will result this row. Okay, again, we have a positive value here. So we have a candidate for the entering variable, which is x2. So x2 will enter as basic variable in next iteration. And in order to decide the leaving variable, again, we have to find the ratios. And this is the least one. So R2 is going to leave in this iteration. And repeat the same process we did in previous iteration. So we have this new tableau of the simplex method. So here we can see that there is no positive coefficient in this row. It means we have achieved the optimal solution. So, and optimal value of this R is 0. So if it is positive, then we'll conclude that the system has no feasible solution and we're done. Otherwise, since this is not positive, this is 0, it should be 0 to proceed with phase 2. So this is 0 in this case. So we are going to proceed with phase 2. So let me write this last tableau again like this. So this is the final optimal tableau of the previous phase. Now we have to solve, this is our objective, actual objective function. So we have to minimize this actual objective function using these constraints and these basic variables. Now these constraints in equation form can be written in this form. Like from this equation, we have coefficient of x1 is 1, so x1 plus 0 x2, so you cannot see x2 here, so 1 over 5 times x3, and we have to eliminate these columns because we are done with it. They have actually performed their duty, so we are going to leave this, and right side is 3 by 5. So this is how we can write this equation from this row, and x2 row will be written as 0x1 plus 1 times x2 minus 3 by 5 x3, and 0x4 is equal to 6 over 5. Similarly, this row can be written in form of equation as 0x1 plus 0x2 plus x3. So you can see x3 here plus x4, which is equal to 1. Now we are going to solve this problem. So we have to minimize this under these constraints, right? So again, let's write the initial table for simplex method. So we have these basic solutions we just found in previous slide, in previous phase rather. Okay, at this step again we need to check the consistency, whether the system is consistent with these with these basic variables or not. If this is not consistent, we have to find a solution to overcome this problem. So let's see first of all whether this system is consistent or not. We have x1 is equal to 3 by 5, we have x2 is equal to 6 by 5, and we have x4 which is equal to 1. Now this objective function depends upon x1 and x2. When we plug in these values, 4 times 3 over 5 plus 6 over 5, and this actually leads us to z is equal to 12 over 5 plus 6 over 5, that is equal to 18 over 5. But we have written 0 here, so it means system is not consistent with these basic solutions. So we have to eliminate these variables from the objective function, and for this this equation gives us value of x1, which is equal to 3 by 5 minus 1 by 5 x3, and this gives us value of x2, which is equal to 6 over 5 plus 3 over 5 x3. So just substitute these values into this z. Z is equal to 4 times x1 is 3 by 5 minus 1 over 5 x3 and plus x2. Plus x2 is 6 over 5 plus 3 by 5 x3. So just simplify this. This is equal to 12 over 5 plus 6 over 5. So let me write constants first. And then we have negative 4 by 5 x3 and plus 3 by 5 x3. And after simplification, we have 18 over 5 minus 1 over 5 x3. Okay. All right. And new 0 will be z plus 1 over 5 x3 is equal to 18 over 5. So let's write these coefficients in the new 0. So we have this. So 1 over 5 here, 0 here, 0 here, 0 here, and we have 18 over 5. Now this system is consistent, and rest of the rows are same. Okay, now we'll again proceed with the iterative process of simplex method in order to obtain an optimal solution. And since this problem is minimization problem and we have a positive coefficient in 0, it means this is not an optimal solution. So this x3 will be entered as basic variables, and let's see which of the variables is will be leaving. X4 will be leaving, and again by the same process, Gauss-Jordan row operations, we obtain this table. And this is optimal because there is no positive coefficient in 0. So our optimal solution is x1 is equal to 2 over 5, x2 is equal to 9 over 5, x3 is equal to 1, and our z is equal to 17 over 5. So that's all.